Hello, all. In the last class, we have discussed different types of integration, namely line integration, surface integration, and as well as volume integration. So, in today, we are going to illustrate the line integration with an example. So, consider this question: find the work done by the force F x by I minus y square j to move the object from the position x equal to 0, y equal to 0 to x equal to 2, y equal to 1 through paths A and B as shown in figure. So different paths are shown in figure, the path A and path B. So we have to find the work through both the paths. That is, first we can find through the path A, then we can find through the path B. Now this is the work done, and we know that the work done is nothing but the line integration of the force. Okay, so the work to move the object from some initial point I to the final point F, we can write as F dot dl. Okay, so F is already known to us. The F is x by I minus y square j. And how we can write dl? dl can be written as dxi plus dyj, because dl is infinitesimal line element, so in general we can write it as dxi plus dyj. Okay, then how we can write f dot dl? F dot dl would be xy times dx minus y square dy. Okay, now I have to integrate this f dot dl through path A and as well as through path B. So first we can do through path A. Okay, so through path A, the W is integral from initial position 0, 0, final position 2, comma 1, and f dot dl would be xy dx minus y square dy. So this integration can be split into two integration. One is integration over x. So the x varies from 0 to 2, x times y dx minus integral y varies from 0 to 1, y square dy. Okay, so we have two integration here. One is integration over x, another is integration over y. Okay, so there is no problem for integration over y because there is only one variable present here, only y is present. So the integration of y square with respect to y is well known to us. So there is no problem for that integration. But how will you perform this integration? That is integral xy dx. So here the integration variable is x, but the function has both x and y. So we have to write y in terms of x in order to perform this integration. So how will we do that? Okay, so for that we can use this information because we are integrating over the path A. So this path A is a straight line connecting 0, 0 to 2, 1. So any straight line in general can be written as y is equal to mx plus c. Okay, so this is the straight line general equation. So if once you know C and M, will get the straight line equation for this path A. Okay, from which we'll get the connection between y and x, and we can substitute that y there in terms of x. Then thereafter we can integrate it. Okay, so our first aim is to find the equation for this straight line of path A. So how will we do that? Okay, so we know that so we can find this M and C by using the conditions, the initial condition or boundary conditions. So we at x equal to 0, we know that y is equal to 0. Okay, so we can choose two different points in this line. So 0, 0 and 2, 1 can be two different points in this line. So when x equal to 0, the y is equal to 0. So y equal to 0 when x is 0. So this implies C is 0. Okay. Now we can take the another point. Then the next point says that when x equal to 2, y is 1. This y is equal to 1 when x is equal to 2. C is already 0. So this implies m is equal to 1 by 2. So therefore, the equation for this straight line y is equal to x by 2. So we can use this relation between the y and x to substitute over here. So therefore, the work done will become the integral 0 to 2 x times y. Instead of y, we can write x by 2 dx minus integral 0 to 1 y square dy. Okay, so this equal to integral 0 to 2, half can be taken outside, x square dx minus integral 0 to 1 y square dy is equal to half. If integrate x square, we'll get x cube by 3 with limit 0 to 2 minus if you integrate y square, we'll get y cube by 3 limit 0 to 1. So therefore this is equal to half 2 cube divided by 3 minus 1 by 3. So equal to 2 square by 3 is become 4 by 3 minus 1 by 3. So the final answer is, sorry, the final answer is 3 by 3, and therefore it will be equal to 1. So the work done from the point 0, 0 to the position 2, 1 through the path A is 1. So W work done through the path A is 1. Now similarly we can find the work done through the path B. So actually the path B starts from 0, 0, reaches here, which is this point, then it reaches the final point. Okay, so this is our initial point, this is our final point, but there is an intermediate point here. Okay, so how we can perform that integration? So this integration can be split into two parts. One is the integral from I to this point. Okay, so this point we can denote it as P. So the integration from I to P, then integration from P to F. Because when we are integrating from I to P, the x is constant, there is no variation in x. And when you are integrating from P to F, the x varies and y remains constant. Okay, so next we can discuss the same integration over the path B. So I will draw the path B over here. So from we have to integrate from I to P, then P to F, so that reaches the final point. So this is your path B. Okay. So first we can integrate from I to P. When you are integrating from I to P, what is the expression for dl? So in general, dl is dxi plus dyj. But from I to P, the x is constant. So therefore, there is no dx. The dx would be 0. And hence, the dl is simply dy times j. Then what would be our integration? So the w, first we can do from I to P. It is x equal to 0, y equal to 0, to x equal to 0, y equal to 1. And that integration is, okay, so that we can write x by dx minus y square dy. X by dx minus y square dy, but there is no dx here, so this becomes 0, and we have only the integration over y, so it becomes minus integral y square dy, and here y varies from only 0 to 1. Okay, so there is no problem for this integration. So in this integration, we can simply integrate it. So y square integrate, we'll get y cube by 3, limit 0 to 1, and it would be minus 1 by 3. So this is the work from I to P. So similarly, we have to find the work from P to F. So work from P to F, the starting point is x equal to 0, y equal to 1, to x equal to 2 to y equal to 1, and integration is xy dx minus y square dy. Okay, now from P to F, y is equal to 1, y is constant, so therefore dy equal to 0 and x changes. So therefore this integration would be integral, we no need to take this dy integration, so dy integration would vanish there, and we have xy dx, but in which the y is always 1, y is equal to 1. Therefore, that integration we can write x times dx and limit from 0 to 2. Okay, so this would become x square by 2 from 0 to 2, where 4 by 2 equal to 2. So that is integration from P to F. Then what is the total work? Total work over the path to B, that is the work from I to P and work from P to F. The work from I to P is minus 1 by 3 plus P to F is 2 by 3. So it will be equal to minus 1 plus 6 by 3, which is equal to 5 by 3. Okay, so work done to the path B is 5 by 3. Okay, so earlier we have already found the work through the path A, and work through the path B is 5 by 3. So work through the path A and work through the path B are not same. So that is, in general, the line integral depends upon the path you follow. Okay, so in general, the line integration depending upon the path. So if you integrate the f dot dl over the path, we are getting 1, over the path A we are getting 1, or the path B we are getting 5 by 3. So it depends on path. Remember, the initial point and final point are same here. Okay, so this we can note down here. In general, line integration depends on path. Okay, but however, there are some special conditions, some special situations in which for certain vector field, the line integration would be independent on path. So such kind of the line integration or such kind of the vector are called the conservative vector field. Now for some vector field, the line integral will be independent on path of integration. Such vector fields are known as conservative vector field. Okay, so then situation is this. Suppose you have some vector field V, some vector field V, suppose it is conservative. Then if you integrate that vector field from some point A to the point B, okay, so suppose you are performing the integration over this path. So maybe this path I can write path 1, or we can find the same integration over another path over the path 2. So if V is conservative, if V is conservative, then integral V dot dl over the path 1 is also equal to integral V dot dl over the path 2. Okay, so better way I can write integral from A to B to the path 1, integral A to B to the path 2 are same. Okay, now this path 2 integration, we can change the limit of integration. If we change the limit from B to A, we can put a minus sign. Okay, so the integration from A to B through the path 1 is same as minus integral of integration from B to A through the path 2. Okay, so if you take this to the left side, last term to the left side, then we can write integration from A to B V dot dl through the path 1 plus integral from B to A V dot dl through the path 2 equals 0. So what that means? So if you're integrating from A to B, if you're integrating from A to B, then from B to A will get 0. So which is actually a closed integration. So the closed integral V dot dl equal to 0. The closed integration means the integration of the closed path. So integration over a closed path is 0 only when V is conservative. Okay, so that is what is meant by the conservative vector field. Okay, so that's all about the line integration. So in the next class, we'll discuss about the surface integration.